Hi, welcome back to physics. This is the waves chapter, where we're studying about disturbances caused by the vibrations of particles, which send energy through the universe without moving matter. Most recently, we've been looking at the way that light waves, in particular, will change their direction of travel as they change from one material, or one medium, to another. This is the concept of refraction. It's a big piece of this chapter. So let's try a practice problem or three here. We'll send a ray of monochromatic light, frequency 5.09 times 10 to the 14 hertz, through some corn oil. Now, you may remember that the frequency of light, that 5.09 times 10 to the 14 measurement, that tells you what sort of light this is. This one in particular, you could look up on your reference table, that's yellow light, right in the middle of the visible spectrum. So we're good scientists, and we measure the speed that light's traveling, and we see that it's moving 2.04 times 10 to the 8 meters per second through that oil. What does that mean? Oil slows it down, and we can use the index of refraction equation, n equals c over v, to find something out about that. So let's use that. We'll substitute in the speed of light c, 3.0 times 10 to the 8 meters per second, as well as v, the speed of light in that other material, the corn oil. Using that ratio, we find that n for this material is going to be 1.47. Notice that there's no units on this because it's a dimensionless ratio of two speeds. Shall we try another? Second ray of light. We use the same frequency, 5.09 times 10 to the 14 hertz. This time send it through some water. Now we happen to know the index of refraction of water. It's given here, but even if it wasn't, you could look it up on your reference table. It's 1.33. So, how fast does light move through water? Well, we can use the same equation, same relation, since this time we're given n. Again, that ratio, 1.33, is going to be equal to 3 times 10 to the 8 meters per second on the top, divided by v, the unknown speed of light in water on the bottom. Solving through algebraically, we see that that light speed goes down to 2.26 times 10 to the 8 meters per second. Quite fast, but also quite a bit slower than normal. Let's change materials again. Dump out that oil, dump out the water. Let's take a look at some glycerol. Send our same laser beam, 5.09 times 10 to the 14th hertz light, right through a container of glycerol. How fast do we expect it to be moving? Now this time we're not given any information, but you already know that you could find this, right? Go to your reference table, take a look up. What is n for glycerol? Page. I see that it's a 1.47. So, just like before, we'll use that equation, n equals c over v, to solve through with 1.47 as our n, to give us a speed in glycerol of 2.04 times 10 to the 8 meters per second. So notice that n for glycerol is larger than n for water, and v, the speed that light moves through it, is smaller. So there's that backwards or inverse relationship between those two quantities. As a final check, let's try this one more time using diamond as the unknown material. How fast does light move in a diamond? I'm not going to give you the answer to this one. I'd like you to pause the video for a moment and see if you can work it out for yourself. So to recap what we've been doing in physics so far, we have waves encountering changes in material. They're going to do two things. Part of the energy of that wave will be reflected to stay in the original material. And as we know from the law of reflection, the angle of incidence equals the angle of reflection exactly. Also, part of the energy of that wave will be transmitted to the new material, where it will experience refraction, which is a change in angle based on two things: the angle of the light ray and the index of refraction for both the beginning and the ending material. One other thing to point out about these transitions is that when electromagnetic waves travel from one material to another, one thing that doesn't change is that frequency. So red light is red light, whether it's moving through the air or through your pool or the glass of water in your hand or any other material. The frequency will be the same, but since the speed does change, we know that the wavelength must also be changing. So if that speed goes down, if the light's slowing down, then the wavelengths will also get shorter, whereas that frequency will be the same. And as a final recap, all electromagnetic waves traveling in a vacuum move at exactly the same speed, which is called c, 3 times 10 to the 8 meters per second. We know that all electromagnetic waves are caused by some form of acceleration with a charged particle. And we know that all electromagnetic waves are made of the same stuff. So the only difference between X-rays, the light you see, infrared, or anything else is the frequency and therefore the wavelength. Thanks for learning with me today. And just as your final check-in, the speed of light in diamond is 1.24 times 10 to the 8 meters per second. If that's what you calculated, congratulations! You get a cookie.